Our protocol duly observed. I'm Adedowole, Alimi from Ajasin University, Akungba-Akoko, Nigeria. I'm here presenting paper titled Force Vibration of Variable Cross-Section Beam Subjected to Time Varying Moving Load. Force vibration of a variable cross-section beam subjected to a time varying moving load is investigated. The Galerkin method is employed to solve the equation of the motion to obtain the dynamic response of the variable cross-section beam. Simply supported end condition for the beam is considered here. Analysis of the solutions obtained were carried out and various results were displayed in plotted curve. A beam is a structural element which is widely used in the engineering, ranging from civil to mechanical and industry for various structural needs. Various techniques have been presented to forecast the dynamic performance of beam under various classes of moving load. Fibers investigated diverse analytical solutions for vibration problems of various end conditions under traveling load. When external bodies act on the beam, this will make it to vibrate intensively and which in various cases vibrate with massive amplitude. Appraisal of huge amplitude vibration of structural elements is very essential in relation to rigidity enhancement. Therefore, the study of the effect of external forces acting on structural members has drawn the attention of many researchers. The problem, we are assuming a non-uniform simply supported beam with length L subjected to time varying load. The structural equation of the motion is specified by the fourth order partial differential equation given in equation 1. Then the end condition, we are considering a simply supported beam here. The end condition is given as in equation 2 and 3, while the initial condition of the beam is given in equation 4. The distribution of the non-prismatic characteristic may be assumed as a power function. The moment of inertia and the mass per unit length is given as a power function in equation 5. The distribution model of the load is given as a delta distribution as given in equation 6. The mass of the load dependent on time along S is given by equation 6b. Then substituting equation 6b into equation 6, we have equation 7. This is the diagram for a load traveling from one end to another end. As it's traveling, other materials and other loads have been added. As you can see in the diagram above, as it travels, the load increase in weight. The problem solution. An elegant solution method called Galerkin method is generally representatively written in the form as given in equation 6, while the solution of equation 1 is represented by equation 9. Y subscript A are the coordinates in modal space, while P subscript A are normal mode of the beam vibration and is given as equation 10. Here we are considering the simply supported end condition. So we have the values in equation 11. Thus, equation 9 can be written as given in equation 14. Then substituting equation 5, 7, and 14 in equation 1, we have equation 15. To determine the coordinate in modal space, so we multiply equation 15 all through by sine j pi x all over x. So we arrive at equation 15. Then in rearranging equation 17 above, we have equation 18. Through Laplace transformation and convolution theorem, equation 18 will yield equation 24. Then further evaluation of integral In equation 24, equation above becomes equation 27. Take into consideration equation 27 above, our expression in equation 14 will give equation 28. Equation 28 above represents the beam vertical response under time varying load. We consider the second case. And second case, we have a harmonic variable magnitude load. The moving force of harmonic variable magnitude load is given as equation 9. Just like in the first case, all parameters remain the same. Consider previous equation 1. Take into account equation 29. We have equation 30, where our omega is omega in the right hand side is the circular frequency of the harmonic force. Equation 30 stands for the main equation of the beam subjected to time varying harmonic moving force. The same procedure is employed in previous case. The procedure is defined by equation 31. The R particle of the system of the time varying load gives equation 30. Translation of equation 33 gives equation 34. Using convolution theorem, equation 34 yields equation 36, as you can see below. Evaluating integral in the above equation, then equation 36 will yield equation 39. Inversion of equation above will yield equation 40. Equation 40 now is the transverse deflection of variable cross-section beam subjected to time varying harmonic moving load. State of the resonance. The equation in 28 represents transverse displacement of structure subjected to time varying load, and while equation 40 stands for the structural response of the beam carrying time varying harmonic load. We are investigating it practically now. In equation 28, the beam will experience resonance effect when we have the condition as given in equation 41. Then for the beam carrying harmonic variable magnitude load, we experience resonance effect in equation 40 whenever we have the condition as given in equation 42. Then the process graph now. Figure 1. Figure 1 represents the force vibration of variable cross-section beam subjected to time varying loads, while other parameters are fixed and they are kept constant. We vary the value of our foundational modeling. As you can see, as we increase the foundation modeling, then the amplitude of deflection decreases. In figure 2, here we consider a force vibration of variable cross-section beam underneath time varying load with various beam increasing factor. As we increase the beam increasing factors here, the deflection and the amplitude of deflection reduces. Consider the figure 3. Force vibration of variable cross-section beam under time varying load with various load increasing factor. You can see here, as we increase the load increasing factor, the deflection increases. Ditto, we also consider for the harmonic, very harmonic variable load. Figure 4 represents the force vibration of variable cross-section beam underneath time varying harmonic variable load with various foundation modeling. So also as we increase the foundation modeling here, so also the deflection profile, the amplitude of deflection also reduces. Also consider figure 5. Force vibration of variable cross-section beam underneath time harmonic variable load with beam increasing factor. As we also increase the beam increasing factor, the deflection reduces. We consider then figure 6. Force vibration of variable cross-section beam underneath time varying harmonic variable load with load increasing factor. Also, as we increase the load increasing factor here, so also the deflection of the beam, the amplitude of deflection increases. Conclusion. In the present work, the authors extended the study of force vibration response of variable cross-section beam when the load is no more uniform. Constant and harmonic variable magnitude of the load cases are presented. The non-uniformity of the load is considered as power function. The equation of the beam of the structure is solved using Gallatin method. The obtained solution are used to determine the effect of load increasing factor, beam increasing factor, and the foundation modulus were determined through the obtained solution. At the end of this work, 1, we discover that the amplitude of deflection magnifies whenever the magnitude of the foundation modulus is intensified. 2, the risk of resonance rises whenever the magnitude of the load increasing factor heightens. Then 3, the risk of resonance reduces whenever the magnitude of the beam increasing factor increases. These are the references. Thanks for listening.